Okay, good morning. This is our last lecture. So today we're going to combine Transcardium Yield Criteria and compound loading. So basically today is what this course is all about. This is the learning outcome. We're going to integrate everything together, okay, and actually do real design work. Okay, real design work means design work that you learn from here can actually make a product or design a product, select the material, the correct geometry, be manufactured, and someone standing on the structure will actually last, okay, through static analysis, okay, through static analysis, right? So today I want to go further to explain. So what we'll do is we'll look at Transcardium Yield Criteria, then we'll go into compound loading. Okay, so let's look at Transcardium Yield criteria first. Okay, so we're going to go into Transcar first. So you know why Transcar I use this symbol over here, because to remind you that it is a shearing criteria, okay, or shear criteria. Right. So I'm going to draw a diagram, okay, and this diagram have two axes. So I'm going to sketch the diagram over here. And this diagram defines the operating boundaries of Transcar criteria. Okay? The operating boundaries. So on our x-axis, right, this is our stress A. I'll define what is stress A and stress B later on. Okay. And on the y-axis is our stress B. Okay, so you see stress A and stress B. And I'm going to draw lines now. Okay. Bear with me, okay? So I'm going to, as you can see, I'm drawing lines now. And these lines, there are reasons for it, okay? I'm not drawing it for fun. So what you see down here, if I were to label them, this is stress U. Over here is stress U. Over here is minus stress U. And over here is minus stress U. So I'll write this out. You'll be wondering what is stress A and B. So stress A and B are principal stresses. Okay, principal stresses in 3D Mohs circle. Okay, so there are the principal stresses. Okay, so what do I mean by that? So now if I were to draw Mohs circle, 3D Mohs circle, so they're not the same, yeah. So this is your normal stress. Over here, this is your shearing stress. Okay, so if I were to draw 3D Mohs circle, so this is just a sketch. So this is one of the circle. Then you have another circle. Oops, not enough space. You guys will tell me, Eugene, it has to be a circle. You are right. And this is the third circle. Okay. So this point over here, right? Or any point, or not any point, okay? Is your stress A. This point over here is your stress, right? and over here you can call it stress C. Okay, so basically are the principal stresses in a 3D mold circle. Okay, so this is based on Transcardium Yield Criteria. So this stress A over here, right, as you can see, right, correspond to the stress A over here. Okay, stress B correspond to the stress B over here. Okay, so the diagram on the left, okay, it's not the same as mold circle. I want to highlight it's a principal stress diagram. Okay, so or principal stress trend. So what you can see down here, based on Tresca, okay, so based on Tresca, right, there are two conditions, right? Based on Tresca, there are two conditions. So based on Tresca, there are two, okay, Tresca's boundary condition. Or not boundary, operating boundaries, okay? Okay, based on Tresca operating boundary, we know that the tau max is equal to half of stress y, where stress capital Y is the U strength. Okay. And another assumption that Tresca make, as you can see in this diagram, all right, as you can see in the diagram, the U magnitude or the U strength okay, the U strength in tension, okay, the U strength magnitude in tensile and compression are the same. Okay, so that's why if you look at the values, which I'm going to highlight, so compression, tension, right? If you look at the scale of proportion, right, it has 4 small squares on the right hand side the same, and in the vertical scale, okay, the spacing from the 0 point is the same. Okay, so it make the assumption that the tensile and the compression strength is the same. Now this will not work for especially concrete for civil engineers. Okay, civil engineering, you don't, and if you are doing design for concrete, this is not the one to use. The one to use is most criteria, which I don't have time to cover. Okay, but the working principle is the same. Okay, so there are generally 3 very popular ones. So there is Tresca's, Von Mises, and one more is most criteria. Okay, their operating boundaries are about the same. Okay, the only thing that is different is in most criteria that is based for ceramic material or brittle material. The compression is bigger, okay, compared to tensile. Okay, now what does this graph like stress A and stress B mean? So your stress state, okay, must be inside this box over here, or this diagram, or this boundary. Okay, so your principal stresses has to be inside that box. Okay, your principal stresses cannot be inside, not box but space. Okay, this is not a box. I do apologize. So I will draw to you. Okay, what does this actually means? Okay, I'll go slow. Okay, I'll highlight to you what does this actually means. So what I'm going to do is I'm going to copy the diagram. And because I need to draw more and more. Yeah. Okay. So now I'm going to sketch the operating space on mold circle. Okay, I'm going to sketch the operating space in mole circle, right? So this is over here. This is my normal stress, okay, and then this is our shearing stress. Element rotate clockwise, element rotating anti-clockwise. Okay. So now we have our operating boundary, right? On, I will change color. I want you to see the difference. Okay. So over here, we have a value over here where this is our stress U. Over here, this is our minus stress U. Okay. And because we are operating on Transcar, this value is equal to minus stress U divided by 2. Over here is stress U divided by 2. So in a nutshell, that is Transcar criteria in mole circle, okay, graphically. So if we look at this box over here, right, and I'll label this with I want to find how to relate the figure on the left to the figure on the right. That's what I'm trying to do. Okay. So now we have, I'll call this condition number A. Okay, I'll call this condition number A. So condition number A states that stress A is at its tensile yield and stress B is at 0. So if I were to draw the circle now, right? So this is our stress A circle, or condition A mole circle, okay? Right? So you can see over here, okay? So this is my A, right? So the yield is at maximum, right? For stress A, stress B is 0, right? So this is okay. So you can see this point over here where you have A condition for stress A, right? And over here is your A condition for stress B, right? You can see that now. It is very clear. So if I go to the other, wait, is that correct? Yep, the other. If I go to the other, not the other extreme, but if I go to this point over here, okay, right? So this is my condition B, right? So for condition B, the yield or the stress A is still at the same point over here, which I'm making the circle or drawing it with the blue bigger. And stress B will be down here. Okay, so this is B condition for stress B. So now if I were to draw the circle, it is still within the operating boundary. Okay, still within the operating boundary, right? Okay, still with it. So now what you realize, right? So we can do any variation now. Okay, I'm I'm not going to do any more variation. You guys know. So now we realize how. So we realize how these two region works. Okay, these two region works. Now I'm plotting at the boundary because within is straightforward. Okay, within the circle does get smaller. So let's say if I have a point C over here, right? If I have a point C over here, I'm going to use a different color. If I have point C over here, or if I choose a condition over here, which is known as point C, right? So what will happen is point C will be a dot, right? So condition point C, right, will be a dot. You can't get a circle.